everyone. My name is Zhao Ying. I'm a third-year PhD student in the University of Aichi, and my research area is evolutionary reinforcement learning. And today I will introduce one of my research titled Enhancing Environmental Modeling and Maximum Diffusion Reinforcement Learning using Evolutionary Computation for Optimal Performance. And this research has been published in Applied Soft Computing Journal this year. And in reinforcement learning, RL training data is highly temporally correlated, violating the independent assumption. And this is because when an agent takes an action at a certain time step, that action doesn't just affect the next state, it can also influence future states. And the second is sample efficiency is low, especially in continuous control settings. And this makes it hard for IR algorithms to be widely applied in a real-world problem. And the third is model-based IL relies on environment model accuracy, causing error accumulation. And model-based reinforcement learning methods can improve sample efficiency, but their performance heavily depends on the accuracy of the learned environment. So we aim to enhance a maximum diffusion IL by improving its environment model using evolutionary algorithm. And this approach helps overcome local optima and improve sample efficiency without actual environment interactions. And there are many methods to mitigate the issue of temporal correlation, but some limitations still remain. And maximum diffusion IL is a model-based reinforcement learning method that greatly reduces the impact of temporal correlations. And however, its performance is still affected by the quality of the environment model. And evolutionary algorithms have many advantages in RL, so we aim to use the strengths of the evolutionary algorithm to optimize the environment model with it. And let me briefly introduce maximum diffusion IL. First, the agent interacts with the real environment to collect the data and store the data into the replay buffer. And then it builds a model of environment which includes both the transition model and the reward model. And next, it uses a planning algorithm to find a state sequence with maximum path in entropy and the highest total rewards. And finally, decisions are made based on this planned state sequence. And now let me introduce our method. And our method mainly involves the environment model. After the environment model is updated using gradient-based method, the evolution module kicks in, and this module creates a population of environment models. After adding perturbations to the population, we evaluate them and select the elite individuals. And finally, we compare the elite with the original model and update the environment model accordingly. And there are and this is the evolution module, and this is the key components of our study, and it includes the three important mechanisms. And the first is dual scale Gaussian perturbations for local and global exploration. And the second is fitness evaluated using replay buffer only, so it's there's no actual interactions. And the third is performance preserving, and the original model is retained if no better model is found. Now I will explain the evolutionary process in detail. And to build a population of environment model, we clone the original model n times. And the model here is implemented as a neural network. And then we add small scale noise to all of the cloned models, which means adding slight perturbations to the neural network's parameters. And for the remaining n minus r models, we add large scale noise. And meanwhile, we keep one copy of the original environment model unchanged. To evaluate the population, we use the loss value as the fitness. And for the reward model, the loss is a mean square error. And for the transition model, the loss is a negative likelihood. And after adding perturbations to the population of environment model, we need to select the elite individuals. There are three steps. And the first step is select the model with the lowest combined loss. And the second is if the elite outforms the original replace it. And the third is otherwise retain the original model to ensure safe updates. And although we added an evolutionary module, the computational overhead is minimal, and this is because the evolution is periodic and uses offline data from the replay buffer and requiring no extra environmental interactions or gradient computations. And in fact, the evolution process accounts for only 0.06% of the total training time. And most importantly, because it accelerates convergence, the total time to solution is reduced by 44% compared to the baseline. And this is the experiment setup. And the task environment is three continuous control tasks based on Mujoko. They are swimmer, half cheetah, and ant. And they are the robot continuous control task. And they are the they have a high dimensional state action spaces. And the baseline is our method and the maximum diffusion reinforcement learning and SAC and MPPI. And the implementation detail is as follows. And for the every task, we use the different neural networks architecture, and the population size is equal to 20, and the small to large mutation ratio is 3 to 1, and the evolution cycle is every 2,000 environment steps. And the evaluation matrix is average cumulative reward per episode and a relative standard deviation for robustness and 10 independent runs with fixed random seeds. And this is the result. The x-axis shows the number of training steps, and the y-axis shows the cumulative reward. And the higher the better. And the red line in the figure represents our method, and the shaded area is the 95% confidence interval, which reflects the stable of the algorithm. And from the figure, we can see that in the half cheetah tasks, our our method has a significant improvement in both performance and speed. And in the swimmer, our method is slightly better than baselines, converges faster. And in the ant, our method is more stable than SAC, slightly better than maximum diffusion RL. And we quantified the data in the in the figure and summarize it in this table. The both value indicate the best performance. And from the table, we can see our method has the best overall performance across all tasks, and the higher returns and the lower variance demonstrate improved robustness, and especially effective in high dimensional and complex environments. And to ensure our performance gains were not just due to the random chance, we conducted a rigorous statistical analysis. Since the data distribution was not normal, we applied the Wilcoxon signed rank test across the 10 independent bands. As shown in the table, the p-values for all comparisons are less than 0.05. This statistically confirms that our method significantly outperforms the baselines, validating the robustness of our methods. In addition, we also analyzed the perturbation strategy, and this includes using only large perturbations, using only small perturbations, and using both at the same time. And we found that the dual scale perturbations is essential for effective model evolution, and large noise enables broad exploration, and small noise enables the stable fine-tuning, and 3:1 ratio achieves the highest performance and the stability. And we also investigated how the population size affects the evolutionary process. And we compared the population size of 5, 10, and 12 on the half-cheetah task. As you can see in the figure, a small population of 5 is the green line performs poorly due to lack of exploration diversity. However, increasing the size of 20, the red line, yielded the best stability and the highest final returns. And therefore, we select the m equals 20 for our experiments to balance performance with computational cost. And in this study, we proposed an evolutionary model optimization approach to enhance the model fidelity and training stability in maximum diffusion RL. And in the future work, we will extend to other model-based RL framework and explore adaptive or learned perturbation strategies. Yes, thank you.
Okay, so thank you for your presentation. And if you are interested in the research, you can check the details on the first page, right?
Yes.
So you do have the
yes.
EOI. Okay, so if you are interested in the research, you can check these publications and find out more details in the published journal. All right, thank you.
Okay.
Okay, can I start?
Okay.
So, Hello everyone, thanks for being here. My name is Qubin Xiao, and I'm currently a PhD student in this campus and working under my advisor, Professor Pei Yin. So my currently main research interests lie in incorporating the kernel method into the discriminant analysis in order to deal with the nonlinear problems. So today I'd like to share my previous survey work. It is titled a comprehensive review on discriminant analysis for addressing challenges of class level limitations, small sample size, and robustness. So in this review article, I examined how classical and modern discriminant analysis methods to deal with the real world constraints, such as the imbalanced distributed data and data scarcity and noise sensitivity. Okay, so to give you guys a clear overview of today's talk, here's the outline. So firstly, I will introduce the background of this review article, and then I will describe the motivations behind this review, and followed by the comparisons and the representing methods of this article. And next, I will shortly introduce the applications and kernelizations, like how these kind of methods are applied and kernelized related contents. And finally, I will give a conclusion and suggest some study perspectives. Okay, so let's begin from the background. It's like the drawbacks of linear discriminant analysis. It is also called LDA for short. Okay, so let's refer to this table. There are three main types of drawbacks of LDA. The first one is it is inapplicable to the multi-modality data, and it suffers from the small sample size. It is also called SSS for short, by the way. So the last one is it is unrobust. So regarding to the first drawback, in the real world, the data is not distributed balancedly, so LDA may, it may lead to the data to be distorted or inseparable. And for the second drawback, it may lead to the severe instability and overfitting, maybe. So regarding to the unrobustness, it may cause the projection vectors to drifting from the target directions, and maybe more severely, like to cause the lower accuracies when doing the classification. Okay, so covering this background content, now we can look at the motivations behind this review. So based on the review of the articles on how to suppress these affections of three drawbacks of LDA, firstly, I aim to provide the basic knowledge about these methods, about how they exist and their philosophies, the solutions, and the related applications. And secondly, I want the readers to know how the methods work in machine learning based on different benefits and usage. Okay, and the last one is most importantly, I want to predict the heading directions in the discriminative analysis area. Okay, this is the motivations. Okay, now let's turn to the comparisons on the representative methods. So based on this, regarding to these three drawbacks, the first one, so we summarized and compared the methods to deal with three drawbacks. The first one I mentioned before is for the multimodal classes, and the second one is for dealing with the SSS problem. The last one is for handle the unrobustness. So, and we compared the methods in terms of some metrics, their general types, the goals, the techniques they applied, and the advantages and maybe the disadvantage. For example, so for the methods handling the multimodal classes, the main types of the methods is like mixture of Gaussians, manifold, second ways, Kn, and the reserve. Okay, so this is the the general introduction of the comparisons of the methods. Okay, now let's turn to the applications and kernelization. So I will shortly introduce this part contents. So in terms of the applications, we additionally reviewed 84 references in order to investigate what kind of field or scenarios these methods are applied into. So the categories goes across the face recognition, fault detection and diagnosis, system condition monitoring, and process monitoring, and so on. So now it is related to the kernelization. So as I mentioned before, my research topic is kernelization. So I have to introduce briefly and shortly, like what is the so-called kernelization. So what is the so-called kernel method? We can refer to this simple image. So in this is a two-dimensional space, right? And there are two classes, the stars and dots. So if we want to separate these two classes, we have to use a circle, which is a nonlinear problem, which is like complicated, right? So, but we can use the feature map to project the data into a three-dimensional space here. So now we can separate these two classes by a flat, so which is a linear problem. It is simplified. Okay, so the feature map is realized by the kernel function. This is called kernel method. This is the equation is listed here. So for the kernel function, its input is the inner products of two vectors in original space, and its output is the result of the inner product here from the feature space. So okay, so the general process is like the data from original original space to the data in the feature space, right? And so from lower dimensional space to higher dimensional space with the dimensional increase and by the feature map. And the problem transferred from linearly inseparable into linearly separable. So this is the very brief introduction of how kernel methods work. So let's back to this kernelization related content. So we also summarized what kind of methods have been extended to kernel version to solve the nonlinear problems. Okay, this is our part of the job. Okay, so now let's we come to the final part, the conclusions and study perspectives in this review article. So totally we reviewed 197 articles, following some priorities like the stronger relevance, a higher number of citations, and more recent publication years, and a higher ranking of journals according to JCR and CSF recommendations. Okay, we can refer to this image. It displayed the revealed methods. Okay, it displayed the categories across by the revealed methods. Okay, so we can find the most of the methods fall into this category. It is that computer science, artificial intelligence. So the second largest category is engineering, electrical, electronic. Sorry, it's not clear. Okay, so and about this review article, I concluded three critical study perspectives. So the first one is, the application areas of the reviewed articles can give a guidance on how, what kind of field, what kind of scenarios these methods are appropriate and can perform best. Okay, this is the first point. The second one is, in the process of review, I also find like there is a form called fusion for the discriminative methods, which is more robust, more stable, and a better generalization. And we also found like there are two types of fusion methods. The first one is combining the objectives of different algorithms. Is like merging. It's merging different objectives. Okay. So the second one is the staged usage of different algorithms. Is like phase by phase, different phase using different algorithms. Okay, this is the second point. The last point is more like a future perspectives. So as aforementioned, we summarize what kind of methods have been extended to the kernel version, right? So it can be regarded as the future topics, like to extend the Riemann methods into kernel version, right? To extend to kernelization. So in order to improve the robustness for nonlinear problems and to handle the multimodal data and to address the SSS problem in kernel space. Okay, so it is worth to mentioning that the second point generates my subsequent research topic. Okay, from the first type, it is combining the merging the different objectives as a new method and extend to the kernel version and apply the proposal into real world scenarios like imbalanced data, imbalanced class distributions data, okay, and the SSS problem and like the data with noise. Okay, so that's it. This is my presentation. So thank you, and your comments, welcome.
Thank you very much for summarizing your research.
Mm-hmm.
So this is your first paper, right?
Yeah, survey paper, yes.
Okay, good.
Yeah,
so
previous.
Yeah, so if you do interested in continue your study in master or in PhD, you have to do like this, right? So it's pretty good research from personal opinion. So you do know down the details, right? For the paper details, do you have the
Paper details, okay,
Do you have
I just show the title, so
Yeah.
maybe you can Google, yeah. So
Yeah, you
this
can note
one.
down the title.
Mhm. Yeah, discriminant analysis methods for classification.
Which
Yeah.
journal? Which journal?
So yeah, it's like no, it's like not very good journal.
Not very good journal.
Yeah.
LQ1 or
LQ, I don't know, I'm not sure. Yeah, in the like fast pace. So
okay.
okay.
Anyway, it's a journal paper, so yeah, it's worth the reading. All right, thank you very much for your presentation. Thank you. All right, so this is the 4 presentations for today. So any things that we have to? No?
I think no.
Okay. Okay, good. So we will end this session here.